So let's start with this one, TK. We'll just be more systematic with this, TK. We're going to start with this one. Starting with the first question. This is W21 question paper 4.3. TK. We're going to start with this one, and we can probably try and do the end questions first. TK, the organic ones. So starting with this question, give the number of. So I'm going to start with question number 7. TK, and let me write this question number 7. TK, so we're starting with question number 7. So there's a structure of phenyl ethanoic acid. TK, that's phenyl ethanoic acid, and phenyl ethanoic acid is so phenyl ethanoic acid is the molecule is given, give the number of different peaks in the carbon-13 NMR spectrum of phenyl ethanoic acid. So you always get this very small question on carbon-13 NMR. So the idea is that if you have a different carbon environment, it will resonate at a different frequency. So if you look at all these carbon atoms, TK, you've got a carbon atom over here, you've got a carbon atom over here, carbons over here, carbons, carbon, this is a carbon, and this one is also a carbon. So you've got a bunch of carbon atoms. Which of these carbons are exactly in the same environment? So starting with the carbon over here, there's no carbon that is exactly the same as this carbon. All the carbons, they are different. If you look at these two carbons, the ones on the right next to it, I mean, this one and this one, they're in exactly the same environment. They're bonded in exactly the same way. This carbon and this carbon, the surrounding environment is exactly the same. Then the next one. Okay, next one is these two carbons have exactly the same environment. This one as well. Then you have the other ones. You've got this carbon, which is yellow, man. That's a different environment. And the last two, they both have different environments as well. So the last two also have, I mean, you got this one and this one, they're all different environments. So basically, they're going to resonate at frequency, let's say frequency F1. These two will resonate together at frequency F2. These two will resonate at frequency F3. This will resonate at frequency F4. This will resonate at frequency F5, and this will resonate at frequency F6. So the number of peaks is going to be 6. So remember, you have to, when you're looking at carbon-13 NMR, if there's only a very slight difference in bonding, the carbon will resonate at a different frequency. This is carboxylic acid carbon. This is a CH2 carbon that's next to a carboxylic acid. There's no other carbon that's similar to this. This is a carbon that's at this point, no other carbon is similar to this one. So they're all different. Is this first part clear? You're going to have, is this clear?
Yes, sir.
So then you have the next question, which is you have to compare the acidity of the relative acidities of the three compounds. So first one is ethanoic acid. Remember, carboxylic acids are by default the strongest acids, relatively speaking. And alcohols, ethanol, it happens to, alcohols are the weakest acids. They don't even classify as acids. They have a very weak tendency to lose H+1 ions. And then you have phenols in the middle. Phenol is C6H5 and OH. Remember, if you check the notes, what happens is that why is this the case? The first one, let's start with it. Alcohols. The problem with alcohols is that when they lose H+1 ions, in alcohol's case, what happens is, and remember, it's the same exact concept that they're going to use, that the carbon chain has an electron donating effect, which is why the negative charge density on this oxygen will increase. So the attraction between H+1 and this O will be stronger. The negative charge is going to be, it's going to be large because the carbon chain has an electron donating effect. And the H+1 will be very strongly attracted to this oxygen. Similarly, if you have benzene, if you have a phenol, what happens in that case? In phenol, what happens is that the H is lost, but the electrons, they kind of overlap with benzene's pi electron cloud. And the negative charge becomes small. And which is why the H+1 is no longer attracted to the O-1, which is why it's easier to dissociate, it's easier to ionize. And which is why there's going to be a lot of H+1 lost. And the carboxylic acid, why are they the strongest acid? Because the reason they're the strongest acid is because when a carboxylic acid loses an H+1, there's a very strong electron withdrawing effect, and this thing becomes very small. The charge becomes very small, and there's hardly any attraction between H+1 and OH, and the OH bond becomes weaker. So what's going on? I mean, this is exactly what you're going to write. I'll just open the notes as well. The only thing you're going to describe is over here, 1 mark will be for alkyl chain having an electron donating effect. The negative charge density on this ion increases and it becomes unstable, or the OH bond strength increases. There's a very strong attraction between the O and H, so less dissociation. Over here, the double bond O, the carbonyl group has a strong electron withdrawing effect, which is why the negative charge density becomes very small. It decreases and it becomes very stable. It no longer attracts the H+1. So the OH bond becomes weaker in size. नहीं बस जो क्वेश्चन नंबर 7 कर रहे हैं अगला जो भी होगा वो फिर उसके हिसाब से होगा अच्छा so you're going to talk about that, and if you were to, you could either mention this one and this one, okay? That would be sufficient. You can just give a small hint that the lone pairs on oxygen, or the negative charge on oxygen, overlaps with benzene's pi electron cloud, which is why it becomes smaller as well, and which is why it's more acidic. It's got just a quick revision of this. Just a second. You get a lot of questions on comparison of so you get a lot of questions on comparison of acids. So yahan pe there's let me just open the right after electrophilic substitution, hydrolysis, and this one. So you get a lot of questions about which acids are strong and which acids are weak. Remember, ethanol, very weak, only reacts with sodium, no other reaction, neither with NaOH, neither with Na2CO3 or with NH3. Phenols react with, phenols, they react with, just a second. Phenols, they react with Na and NaOH, and no reaction with this one. And carboxylic acids, they have all reactions. Then you have the next thing. Let's move to the next question, which is it's the same question. Next part. So write an equation of reaction between chloromethane and AlCl3. He's given you that chloromethane reacts with AlCl3. Chloromethane is this thing, it's CH3Cl. It reacts with AlCl3. He's told you that one of the carbocation is formed, so it's going to form CH3 plus 1. And AlCl4 minus 1 is going to be your other product. Then he says, draw the mechanism for electrophilic substitution. Draw the mechanism between CH3 plus 1. This is a very standard mechanism that is going to be asked over and over again. And this standard mechanism is this one, electrophilic substitution. So it's this mechanism, electrophilic substitution. What happens is that you have a positive thing attracted to the benzene, and that positive thing is going to bond with it. The carbon electron cloud on the benzene will become partial, and then the H will give electrons back to it. So it's a very standard mechanism for electrophilic substitution. So you just have to draw that. So that CH3+1 is going to come in. It's going to bond with one of the carbons, and the electron cloud will become partial. This is, if I just go over this mechanism, this is electrophilic substitution. What happens in electrophilic substitution is you've got a benzene electron cloud, and the electrophile attacks it, takes away one of the p orbitals and bonds with it. So the carbon is now without one p orbital. So the electron cloud is now partial. It's got a positive charge, and the H then gives the electron back. When it gives the electron back, the electron cloud reappears. So that is what electrophilic substitution is. There was nitration as well. Same thing happens. NO2+1 comes in, takes away the p orbital, bonds with the carbon. The electron cloud becomes partial. You get a positive charge. And then what happens is that the H gives the electron back. So the electron cloud reforms. So this is a very standard mechanism for electrophilic substitution. And so they'll ask you to draw any electrophilic substitution mechanism with any electrophile. Over here, it's CH3+1. Okay. Now there's a 3-step synthesis of phenylethanoic acid from methyl benzene. State reagents for step number 1. Now, step number 1 is whenever you have a Br that is getting attached, it's not getting attached to the carbon chain, it's getting attached. So it's not getting attached to the benzene, it's getting attached to the carbon chain. Whenever it gets attached to the carbon chain, that's a UV light reaction. ठीक है, वो यहाँ पे इधर spider chart में it's given as well. Okay, whenever you have Cl2 whenever you have an alkyl benzene and the Cl gets attached on the carbon chain, that's a UV light reaction. It's Cl2 or Br2 under UV light. So it's this reaction. So it's going to be bromine plus the conditions are going to be, it's going to be UV light. Suggest the structure of compound Q. So you're going all the way from this point to this point. So first thing is there's an increase in carbon chain length. The only way the carbon chain length increases is that you've got a CN attached to it. So the Br gets substituted by a CN. So there's a CN now attached where the Br was attached. So this was nucleophilic substitution, and this was AS. AS was that when you have a halogenoalkane, NaCN ethanolic and reflux, it will give you a nitrile. Now, the purpose of the reaction was to increase the length of the carbon chain, and that is exactly what happened over here, that you had a longer carbon chain, so which is why there was definitely a CN attached. And this one, the step 2 reagent would be NaCN. And it's going to be ethanolic. Conditions, we've already told the conditions for step 2. And also step 3, how does the CN turn into a carboxylic acid? That is also AS. So how does, once you get a CN, how does it turn into a carboxylic acid? That is dilute acid and hydrolysis, reflux. So this one is dilute H2SO4 or any dilute acid. And reflux. Per organic byproduct that forms in step 1. So what is the organic byproduct that is formed in step 1? Now the thing with UV light reaction was that the Br could, I mean, you had 3 H's with this one. So any of the H's could be substituted, or all three of them could be substituted. So you were not in control of how many BRs will get attached when you had an ultraviolet light reaction, a free radical substitution reaction. So you could have any number of BRs getting attached to this carbon over here. So जो दूसरा byproduct होगा ना, that's going to be you can have 3 BRs. Is that clear? ठीक है Mariam, I'll share the map.
Thank you.
So the organic byproduct is for the reaction number 1 is ultraviolet light, any number of BRs could be substituted. I think it was next one. What is seen when aqueous bromine is added to phenylamine? Okay, so you've got aqueous bromine added to phenylamine. Now that's also electrophilic substitution. Like where's the chart? This one. I said, do you see phenylamine anywhere? It's over here. So what is seen when phenylamine? This is phenylamine. NH2 with benzene. Bromine gets attached to it. Phenylamine, remember, is a very activated benzene. Like if you look at the notes in 246 directing effect, TK, if you look at the detailed notes, where's phenylamine? Just a second. So this one. Now in phenylamine, what happens is whether it's NH2 or whether it's OH, phenol and phenylamine, they're both highly activated because the lone pair on NH2, it overlaps with benzene's pi-electron cloud. When it does that, the electron density over here increases a lot at positions 2, 4, and 6. So the electrophile is very strongly attracted to it. So it's so strongly attracted to it, whether it's phenol or whether it's phenylamine, whether you've got OH or NH2, the bromine gets attached on all 3 positions and you get a white precipitate. Okay, so you're going to get, that's the observation, you're going to get a white precipitate and bromine will get attached to positions 2, 4, and 6. So the answer to this one is what is seen? It's a white precipitate, that's it. And obviously it's 2 marks, so there must be something else. When aqueous bromine is added, the bromine will get decolorized because it's going to react. So red-brown bromine gets decolorized. What is seen when bromine is added to ethylamine? Nothing is seen because the reaction was only for phenylamine, the one with benzene. It was a reaction for benzene. So no reaction over here. Draw the structure of the organic product formed when an excess of aqueous bromine is added to phenylamine. So it's exactly this one. It's phenylamine. Remember, phenylamine, its benzene is very reactive, so it's going to be this one. Even with nitration, it's going to be very reactive. With nitration, if you use concentrated nitric acid, NO2 will get attached to all 3 positions. If you use dilute nitric acid, only 1 position, either 2 or 4. So this is with NH2. So you can draw the product. It's NH2. The lone pairs will overlap. I mean, you don't have to show all this. So the electron density will be higher. So bromine will get attached to positions 2, 4, and 6. Name the product that you've drawn. So that's 2,4,6 tribromo phenylamine. Okay, the name was written over. I mean, this is phenylamine with bromines add 2, 4, and 6. Now the next question. Compound T is made by a 3-stage synthesis. Phenyl ethanoic acid reacts with a suitable reagent to form compound R. So there's R getting formed. What is happening? The OH gets carboxylic acid, turns into an acyl chloride. This is an acyl chloride. So what's the reason for that? The reason for that is, I mean, you can have a look at the chart, PCl3, PCl5. So it's given over here. Carboxylic acid turns into an acyl chloride. It turns into acetyl bond OH. It turns into acetyl bond OCl. So it's either PCl5, PCl3, SOCl2 plus heat, any of them. So that's your reagent. So we're going to go with PCl3 plus heat. And they were just looking for the reagent, not the condition. So I guess just PCl3. Compound R reacts with ethylamine to form compound S. So these two are reacting and they're forming S. So what is happening over here? This is this reaction. It's the formation of amides. So when you have acyl chlorides, if you react an amine with it, the carbon is positive. And let me show you in the notes as well. Just a second. So amide formation, I guess this one. So when you have an acyl chloride acetyl bond OCl, the carbon is partial positive. The N has lone pairs. NH2, they're going to join up. The HCl is going to be formed as a byproduct and they will form an amide. An amide link is going to be formed. So that's the reaction we're talking about over here. Name the functional group. So this is an amide. So this functional group is, and the other product that is formed is HCl. The N will lose the H. The other product is going to be HCl, this one. The H and Cl will get knocked out in the middle. So that's HCl. I said, then you have this one. Compound S reacts with a suitable reagent to form compound T. So an amide is now turning into an amine. So how does an amide turn into an amide? So again, have a look at the chart. How does an amide, you got an amide, and this amide is now turning into an amine. So the double bond O disappears. The oxygen goes and H gets bonded to it. So that's LiLH4 and reduction. So amide turns into, the oxygen just disappears. It just turns into a carbon chain. So the amide turns into an amine, and that's exactly what's happening. You had a double bond O. Now in its place, you got a CH2 basically. So LiAlH4 is the reagent, and that's a reduction reaction. As the next one. As the next one is the relative abundance of the molecular ion peak in the mass spectrum of ethylamine is 62. Calculate the relative abundance of the M+1 in the mass spectrum of ethylamine. So this is about mass spectrum. What happened was that in mass spectrum, ethylamine has 2 carbons. So we already know the number of carbon atoms. Now, there was a formula of calculating the number of carbon atoms based on the M peaks. It was the MM+1 ratio. And that will give you the number of carbon atoms. We already know that it's 2 carbon atoms because they've already told us that it's ethylamine. Now, the formula for finding the number of carbon atoms was that the number of carbon atoms was 100 over 1.1 into M+1 height divided by the M height. Now, over here, the problem is we know the number of carbon atoms, that's 2. So it's 2 over 100 over 1.1 times, we don't know what the M+1 is, but they've given us the height of the molecular ion peak, which is 62. So they've given us the M peak. So okay, what's M+1? He's saying, did anyone try and calculate this? Let's say here 1.364. So I guess the relative abundance of that is going to be, we're getting 1.364. Okay, so remember the height of the M peak is 62, so it's 62 ratio 1.364. Anyways, the mass spectrum of compound T contains several fragments. So when you're doing T क्या चीज है? So T is this one. So this is your molecule T. So he's saying when he did the mass spectrum of T, he got a fragment at 29, he got a fragment at 91 as well. So ढूंढोगे, what is the fragment at 29? And I'll add in the hydrogens. This one will have 3 H's, this one will have 2 H's, 2 H's, 1 H, 1 H, 1 over here, 1 over here, 1 over here. I said 29. So what is 29? I think it's this one. CH3 and CH2, right? And put a positive charge on top of it. So that is, I think that's 29. Okay, that's 29. What is the other one? 91. Can somebody double check, is the rest of the, is this whole thing 91 or not? Okay, how many carbons you got? 6 carbons, 5 hydrogens, C6H5. Then there is CH2, CH2. And then you've got an NH. And we're putting a positive charge on top of it. Can somebody calculate and tell me whether this is 91 or not? क्या value है? That's, this is 120. Like we're looking for 91. This could be fragment. We're looking for a fragment that's 91. So 91 C6H5. That's
Sir, 91 is just the benzene ring and the first methyl.
this part.
Yes.
Okay, then that's, I mean, up till CH2, right? So I guess 91 is C6H5 and CH2.
Yes.
So that's 91. That's the other fragment. Okay, so we had to look for 2 fragments. One was this one. The other one was this one. Or not this one, this. So okay. That's 91. So that's 91. We're done with that. Then you have the proton NMR spectrum of compound T shows hydrogen atoms in different environments. 6 of these environments are shown in the structure using letters A, B, C, D. And so remember, hydrogen resonates at a different frequency if the hydrogen environment is different. So these 3 hydrogens, you got 2 hydrogens over here. You got this hydrogen, you got 2 hydrogens over here as well. 2 hydrogens over here, and there are that's going to be 1, 2, 3, 4, 5 hydrogens over here. So what he's saying is use the letters A, B, C, D, and E, and F to answer the questions that follow. The questions relate to the proton NMR spectrum of T. So the proton D does not cause splitting of the peaks for proton C or E under the conditions used. Do you remember NH and OH, they never cause splitting. So identify the proton or protons with a chemical shift delta in the range of 6 to 9. So who's in the range 6 to 9? For this, you would need you can't say a paper. I know the data booklet is separate. So 6 to 9. Like if you do we have a data booklet? Just a second. As a 6 to 9. So look at the table of this is carbon 13, the HNMR. So 6 to 9 is the benzene H's, 6 to 9. Okay, that's exactly the benzene H's. So he's asking about those. So this is 6 to 9. And that's A. Then he says, identify the proton or protons whose peak will disappear in D2O. The NH peak is the one that disappears in D2O because D+1 amines and alcohol and OH groups, they ionize. So the H's, they get replaced by D+1 if you add them in heavy water, and this does not resonate. So this peak disappears. If the H gets substituted by D, its peak will disappear because it will stop resonating. Identify the proton or protons whose peak is a triplet. So triplet is the neighborhood must have two hydrogens. So it's going to be this one. This is going to be a triplet peak, F. Because its neighbor has two hydrogens. C and D will also be triplets. C and B, sorry. Because the neighborhood of B has two H's, so that's a triplet. The neighborhood of C also has two hydrogens over here. So they're also triplets. So both BC and F, they're all going to be triplet peaks. Remember the N+1 rule was that your peaks are going to split. If the neighborhood has N hydrogens, it will split into N+1. So if it's a triplet, that means the neighbor has two H's. Over here, the neighbor has two H's because there's no neighbor over here. This one has no H's, right? So it only has this neighbor. This one only has these two. So they're both going to be triplet peaks. So it's going to be BC and F. And identify the protons or protons with the lowest chemical shift. The ones that have the lowest chemical shift in the data booklet are the ones which are part of the carbon chain. The CH resonating and are part of the carbon environment, alkyl environment, 0.9 to 1.7. So they've got the lowest. So the ones, so the lowest is going to be this one. F is going to be the lowest because it's part of its neighborhood as a carbon chain. So that's kind of going to be the lowest. So that's it. It's part of the carbon chain. So that's the one. Not this one because their neighbor is NH. This neighbor is benzene. So not these, but this one. Because if your neighbor is NH, the resonant frequency is going to be a lot higher because if your neighbor is, if you've got an electronegative atom next door, alkyl next to an electron, it's going to resonate at 3.2 to 4. So if the neighbor is attached to an alkene or it's next to an aromatic ring, it's going to resonate at 2.3. So if it's next to benzene, it's going to be 2.3 to 3. So only the alkane chain, there's only one of them. So this one is the one that's going to have the lowest peak, the lowest frequency, resonant frequency, chemical shift value. So it's F. This one is F. Okay, is this clear? You clear? Yes or no?
Yes, sir.
Okay, so just remember, okay, NMR spectrum, I mean, there are basically 2-3 things that you have to remember about NMR spectrum. One is the hydrogen environment. So they'll all resonate at a different frequency if the hydrogen environment is different, if the way they're bonding is different. You can have the table will assist you and tell you what values at which they're going to resonate. And then there's a splitting pattern. The splitting pattern is that if the neighborhood has two H's, it's going to be a triplet peak. This E is going to be a quadruplet peak because its neighborhood has three H's. and so on. Okay, B and C, they're going to resonate. I mean, B is going to be a triplet as well. C is going to be a triplet. So that's it. Okay, so so with this one, we did question 7 and 8 so far. So let's continue tomorrow then, okay? Because the next question looks big, okay? So it's going to take a long time. So we'll continue with the same paper next time.
Thank you, sir.
Okay, then take care. Office.